That's, yeah. Don't fuck with your life. Quite literally. That's funny. That's great.
All right, last little bit, all right, of chapter 10 and the material for the course. So we were talking about radicals and we're going to continue to look at simplifying them and then furthermore solving them. The big thing is that radicals can be simplified sometimes and cannot be simplified other times. Sometimes one of the things to do is think about the radical as a variable. So if I let y equal root 2, this equation actually becomes 5 plus y. That cannot be simplified any further. Similarly, if I let x equal root 5 here, this becomes 3x plus 4x. That does simplify to 7x, aka 7 root 5. The radical is a piece attached, all right, to the number, but it's indicating, all right, something that is a like term or an unlike term. Now, obviously, I can see that right here, 3 root 5 plus 4 root 5 is, yes, 7 root 5, all right? I show this just because some people don't combine radicals that are the same. And that's what we want to make sure we can do. You can add them, all right, when there's things underneath radicals, you multiply them. So let's look at some examples. So root 5 plus, okay, and notice our directions, all variables represent positive real numbers, rationalize denominator where appropriate. Those are the two kind of standard directions, all right, for all problems with radicals. All right, so root 5 plus root 20 plus root 7. Initially, it looks like I cannot combine those. Those are all different radicals, all right, so I possibly might not be able to combine them. But root 20 with radicals, all right, the idea is to see if you can simplify the underneath of the radical, then combine them on the outside. So 20, let's do our prime factorization. That's 4 and 5. 5 is prime, but 4 I can break down, 2 and 2. So root 20, I can actually rewrite that as 2 squared times 5. And then remember when there's no number on the index, what number is always hidden? 2. All right. Oh, look, square root and 2 squared means that I can pull
2 out.
a 2 out, and that leaves 2 root 5. So back to our equation, that means this is root 5 plus 2 root 5 plus root 7. 5 and 7 are both prime, so I can't reduce those any further, but I have root 5 plus 2 root 5, which becomes 3 root 5 plus root 7. That's as far as I can go with that. Again, knowing when to stop is just as important as knowing when to keep going. Way too often, right? Oh, it's not, 5 plus root 5 plus root 7 is root 12. No. Okay? These are basically unlike terms, right? That's why I was doing the let them be a variable. It's just a variable that we can do stuff with.
Root 5 minus root 2.
So rationalize the denominator, right? So radicals in the denominator means I have negative exponents, all right? That's something we don't want, so that's why we're always going to be rationalizing the denominator. We want everything to be positive exponents or radicals in the numerator. In order to get rid of this, we need to create a difference of squares. So we can't just multiply by exactly the same thing. I need to multiply by something just slightly different to create a difference of squares, right? This is x minus 3, x plus 3, essentially. That's what I'm creating because when I multiply this out, the radicals will go away. Now again, I need to multiply by the same thing, numerator and denominator, because this whole thing, mess divided by mess is, what is this actually? 1, all right? That's just multiplying by 1, all right? We're not changing anything. Now, here's the other awesome part. How do I multiply that top term? How do I multiply the bottom term? What technique? Box!
You would come for me.
But I have a box on the top and a box in the denominator. So once again, all right, we're approaching the end of the course. Box, diamond, wash the bunny face, grouping, all that, all those techniques, they keep being applied to other stuff. All right, so we have, go ahead.
Oh, wait, that one is a negative, never mind.
I have a box in the numerator and then a box for the denominator, right? So we're doing 2 boxes. All right, so let's start with the numerator. So remember, you multiply into the box, all right? And multiplying radicals gets a little tricky, so you got to be careful. Good news, 4 times root 5 is just 4 root 5. That one's the easiest one. All right, the other easy one is the bottom right corner. Root 2 times root 2. 2. All right. Yeah, because root 2 times root 2 equals root 2 squared, which is just 2. All right. A radical times itself, all right, that's the best part, all right? Just ends up being whatever is underneath the radical, as long as they're both the same. Okay, when I have root 5 times root 2, that's when you get to multiply the underneaths, okay? If they have the same radical, this is square root and square root, then you can multiply the radicands, all right, to simplify them.
That'd be
Root 10. Yeah, it doesn't get any simpler than that. And same thing, all right, 4 times root 2.
4 root 2.
4 root 2. So the tricky part about radicals is knowing, oh, okay, these ones I multiply the underneath, this one I multiply the outside, because this is 1 root 5, right? Times 4, no radical. So that becomes, right, it's 1 times 4, 4 root 5. So when you multiply pieces of the radicand, when you multiply pieces of the outside, that's the part that gets tricky with radicals. All right, similarly, all right, now that we've done the top one is actually more difficult than the bottom one. Because root 5 times root 5.
Root 25.
Correct, root 25, which is 5.
Oh.
Square root of 25 is 5. Yeah. But this is the same principle that we had right here. Root 2 times root 2 is root 2 squared, which is 2. All right. Root 5 times root 5, 5. Same thing. All right. Root 2 times negative root 2.
-2.
Negative 2. So those should be your favorite ones, because when you have the same thing being multiplied,
It just becomes number.
it just becomes itself. And don't forget the sign. Sign is the most important. Brian's not here to pick on. All right. Signs are important. Okay. And then root 5 times negative root 2.
That is negative root 10.
Yes. All right. And remember, the sign stays out front. Negatives underneath the radical is bad news. Root 5 times root 2. Root 10. And then, oh, look, negative root 10, positive root 10. So notice what this radical actually becomes. 3. So this is the denominator box. So notice the denominator is now 3. Any radicals left? No, we have successfully rationalized the denominator. All right, so let's write it out. So the top one is a bit of a mess. All right, we have 4 root 5 plus 4 root 2 plus root 10 plus 2 all over 3. Now, be aware, that's as simple as that gets. All right, none of those terms combine. All right, root 5, root 2, and root 10 are all distinct. Okay, you cannot combine these in any regard. I can't even factor anything out. Can't factor a 2 out because there's no 2 in front of that root 10. Okay? So that is as simple as that gets. But the point was to rationalize the denominator. All right, I have the 4th root of x plus y cubed. Now, in order to make things simpler, can I just bring this 3 in, right? X cubed plus y cubed. No, why not?
Plus y, x plus y plus, yeah, times x.
That means x plus y times x plus y times x plus y. All right, you cannot rainbow, all right, exponents in, not a cross addition. Okay, so, and now here's the thing. I have a 4th root on top and a square root on the bottom, which means I can't just put them under one big radical because these are different indices. All right, so that means that we have to come up with another way to combine these. Does anyone have a suggestion?
No.
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 Multiply the top and bottom by the cube root.
I could absolutely do that. That might make things worse, possibly.
Yeah.
I was like, it'll definitely get worse and it might get better, but it's actually gonna get worse. So that's always a technique. Don't forget, radicals actually represent exponents. So notice my bases are both x plus y, which means this is actually x plus y raised to what power?
2.
3/4. All right. It's already cubed. And this means 1/4, so it's 3/4. All right. What's the exponent of the denominator?
1/2.
Or
1/2.
Sorry.
You are correct. The indice is 2, which makes that 1/2. Ah, now I have same base and same base. And when you have the same bases, what do you do with the exponents when they're being divided? Subtract them.
So that'd be 2/4 to 1/4.
That is correct. And now look, this is all in the numerator. And now I can turn this back into a radical. And it's just 4th root of x plus y. Now, be aware, multiplying by root x plus y over root x plus y, that can slowly combine, but you're never going to have a good method to combine a 4th root and a square root. The only method is to turn them to exponents and then see if you can use powers of exponents.
Seems like a lot of steps just to 3.
Okay, this could have been 8s and 7. Okay, the fact that it just has
No,
a
I know.
3 is
No, I'm
like
just-
coincidence, right?
I'm just saying that, like, looking at it, like, somebody would say it was probably a lot of steps just to erase a 3.
All right, assume they represent positive real numbers and the standard directions are rationalized, but none of these are gonna need rationalization. All right, so in both of these first 2 cases, what do you notice about the radicals? They are the same. right? Which means we can put them under one big radical.
How are they the same?
Fourth root, not same as each other. Numerator and denominator are same. These are three different problems, right? I mean, these are the same. Fourth root.
Okay.
And when I do the next problem, oh, look, third root, I could just see it already.
I thought you meant the whole problem.
Yes,
I was like, they're not the same.
definitely not the same. The first problem, the fourth root problem. So I'm gonna put that under one big radical. Then I can just simplify. Now I'm just doing rules of exponents with stuff underneath the radical. 48 divided by 3. X to the ninth and X. So what power of X is that? It doesn't say.
First.
It's always the first. Which means X to the eighth in the numerator. Y to the 13th and Y to the negative second power.
So wouldn't that be y to the 11th?
Why the 15th?
Y to the 15th. When you bring it up, it actually becomes 13 minus negative 2, which becomes 15. So remember that when you bring this up, and we'll write that one slower, minus negative 2.
Which then makes it positive.
Yes, which makes it,
Okay.
we'll write this one slower too. So remember that, again, all you're doing is subtracting exponents when you are dividing them with the same base. Okay, so this becomes 4. 16, x to the 8th, y to the 15th. And then what should we do?
Split up the exponents so it can easily divide to 4.
Split up the exponents, start matching them to four powers of 4 because we have a fourth root.
X squared.
Let's start with the 16. 2 to the what? Makes 16. Oh, look, what a coincidence. All right. And then, all right, I have x to the 4th and x to the 4th. All right. Those become x to the 8th. How many y's? Let's see. Y to the 4th, y to the 4th, y to the 4th. Do I have another one? Y to the 3rd. Because again, now we're doing the reverse rules of exponents because when you add all these together, they have to make, all right, the combined total of exponents. But
4, 8. 12 plus 8.
we got them, but it's always good. Gotta make sure, always double check. 4 plus 4, oh, that made 8. 4 plus 4, 8, 12, 15. Okay. All right. Make sure that you didn't forget one because we're just breaking them apart. All right. That comes out as 2x, x. I'm going to write it out slower. Y. And then fourth root, what's left under the radical? Y cubed, just a single y cubed. That then becomes 2x squared y cubed, fourth root of y cubed. Now again, like I said, feel free to skip the last time I skipped from this step to this step, everyone hated it, so that's why I did it a little slower. I was like, but feel free to skip any steps that you can successfully skip. And hey, from right here, some people can see, that becomes 2, that's an x squared, y cubed, and there's 3 left. So whatever you see and you can skip. If you get confused, do more steps always. Okay, so just like in our last problem, I have a cube root in the numerator, a cube root in the denominator, which means I can put it all under one big, beautiful cube root. But when I do that, I was like, can I cancel the r's and the s's and I end up with cube plus cube? No. All right. So then I need to think a little bit harder. I got it all under one giant radical, but then I was like, I feel like I want to be able to cancel something. Does anything spring to mind?
R's and S's because they're cubed already. This is over addition.
I cannot. Yes. Okay. There might be another technique. I definitely can't just cancel R and R. That's what I was saying. I was joking. S and S. You cannot do that. You cannot cancel across addition. But I might be able to break this down. R cubed plus S cubed. Does anything spring to mind?
Difference of cubes.
Not a difference.
Sum of cubes.
Sum of cubes, which means what technique do we use to break this down? Wash the bunny face. All right. I love cubics. Okay. Because it's the best part of the dance and they appear everywhere and people just don't recognize them. Recognize the cubics. All right. So let's refresh on our bunny. So that means R cubed plus S cubed. All right, and then how do I determine the signs? When you wash the bunny, you need to make sure you use what? Soap. All right, same, opposite, always positive. All right, so I like to fill in the signs first. I've identified R cubed makes R cubed, S cubed makes S cubed, which means that I have my first two terms, R and S. Whatever you use to make the value cubed, those drop down. And then in order to fill in the bunny, all right, in order to fill in the polynomial, we use the bunny. R times R. R times S. S times S. And we have washed the bunny in order to factor the cubic.
So could we cancel out the RS with the other RS now that it's multiplication?
Yes, see how that works? I'm gonna rewrite it out though. So our factor from above now looks like this. I broke the R cubed plus S cubed into its individual pieces. And then yes, R plus S and R plus S, I can cancel that entire binomial with the entire one in the denominator because they're being multiplied.
Does that just become 3 square root R squared minus RS?
Yes. There is now only a 1 in the denominator, which means I no longer have a fraction. You can't, there's nothing to solve.
Okay. Or
This
you
is-
Factor it. Yeah,
This does not factor.
okay.
This is prime. Once you do cubic,
Oh, yeah.
so once you do the cubic, you can't diamond. If you're down to the stage where you're doing the cubic, this will never be able to be factored. This is prime. Because we can do the diamond on that, right? It won't work, because it'll be 1 and -1. What multiplies the 1 and sums the -1? Nothing. But it is always good to check. That way you could just keep reinforcing it to yourself.
I think I'm just traumatized by that particular quadratic. I feel like I need to do it all the time. Every time we see it in here, I'm like, should we just do it?
Yes, and it's good to always think that way. You're like, I see a quadratic diamond. It should be the first thing that jumps into your head,
Yeah.
right? What? Why is that annoying? That's good. The more math you learn, the more math you see everywhere. I just look around and see equations.
Sounds like a nightmare.
One person's nightmare, another person's dream.
Mostly at teacher's dream. Unstable.
Plus minus, okay. All right, for our last problem here. Initially, on first view, these are three distinct radicals. But we want to simplify the underneath of the radical, the radicand, all right, to see if maybe they do have something in common. So one piece at a time, first radical. Is there anything I can do with x cubed minus x squared? Yes, greatest common factor, all right? The very first step of factoring, all right, is greatest common factoring, the one that is the most overlooked. If I pull out x squared, that leaves x minus 1. While we're at it, let's simplify that down. Even one more step. Square root of x squared is x. So I can actually pull an x out of that. And that leaves x minus 1 underneath the radical.
Yes.
All right, we're going to simplify all of them, just one piece at a time. Same thing, greatest common factor on the next one. 9x squared. Right, they both have a 9.
Yeah, and then.
And then once again, square root of 9x squared. Square root of 9? 3. Square root of x squared? X. So
First term, the x squared, square root of x minus 1, because you pull out 2x.
first term. Where are you looking? This one?
Yeah, because you pull out an x from the first, and then the other x squared, you can also pull out because it turns into a 1.
Yes.
When you get an x squared out of the whole thing?
No, so I'm still underneath the radical here,
Oh, okay.
okay? So greatest common factor, so ignoring the radical, right? I pull out x squared times x is x cubed. X squared times 1 is x squared. Then the step I'm sort of skipping,
That would make just 1x, because x squared is just 1x.
because I'm sort of skipping this, that I'm actually breaking this into 2 individual radicals.
Okay.
Because I say, well, if they're being multiplied, then I can multiply 2 individual radicals. Square root of x squared, oh, it's just x. Square root of x minus 1 I can't do anything with, so it just comes down.
Okay.
And that's the same step that we're on right here. So if you get confused, turn all those multiplications into individual radicals. Because, it's like, as easy as it is, square root of 9x squared, right? I heard 9x, I heard 3x squared. I was like, it happens to all of us. Break it down one piece at a time, and just one piece at a time. Square root of 9, 3. Square root of x squared, x. That just gonna come down because I can't do anything with it. All right, and then lastly, now we're seeing a pattern, right? 4x cubed minus 4x squared, what can I pull out?
4x squared.
4x squared. What's left?
X minus 1.
X minus 1.
We need 2x.
Let's do the extra step. Square root of 4 times square root of x squared times square root x minus 1. That leaves square root of 4.
2.
Square root of x squared.
X.
And then the other piece comes down, x minus 1. And oh, look, now look at the three radicals that started very, very distinct. All right? Do they all have the same radical associated? Which means x plus 3x minus 2x results in 2x root x minus 1. So being able to simplify these seemingly complicated radicals is a big deal because this bottom piece is way simpler than that top piece, even though they are equivalent. All right, last, definitely not least, solving. Notice that just like we did with complex rational expressions, factoring everything, we go through like 5 sections of simplifying something before we get to the simple version of solving it. It's because solving is easier than simplifying as long as you know the properties, okay? If you know the properties of how to solve something, how to simplify something, then solving it is very, very simplistic. The biggest property with solving radicals is to raise it to the equivalent exponent power. This one we've been doing since the start of class without actually talking about it. What is the opposite function of square rooting? Squaring. That's how you get rid of a square root. What's the opposite of a cube root? Cubing. All right, fourth root, fourth thing. So it is that power. The other thing that we're adding in, so if I have something, right, look at that bottom left one, to the 1/3 power, what root is that? Third root. So hence the opposite power.
No.
Cube root. The opposite is cubic. So just be aware that sometimes things are written as fractional exponents, but that's still a cube root there. All right. So let's start with the easy one, and then we're going to go from there. With solving radicals, the other thing to mention, remember that when you simplify, you do PEMDAS, parenthesis, exponent, multiplication, division, addition, subtraction. When you solve an equation, you actually start at the end and work this way. Radicals, aka exponents, are the E. That means that you should do all the simple stuff before you square both sides. That means the first thing I do is subtract 3 from both sides. Isolate the radical first. Because if I try and square it there, I end up having to do box. Then, now I'm here, now I can square both sides.
Then just becomes x equals 4 squared, right? Or
Correct. X equals 4 squared, aka 16. All right, same thing. Isolate the radical. That means I'm going to add 3 to both sides first. Once you have the radical alone, then you can do the opposite radical function. In this case, square root, I'm going to square both sides. Now the good news on the left side, square root of 3x plus 13 squared becomes
3x plus 13.
just the underneath. Okay, so we're seeing that connection. What about on the right side? X plus 3 times x plus 3, all right, aka a super simple box. I'm going to box it out just because to emphasize how beautiful the box is. Even though this is one that you could do in your head, but the box is wonderful.
Punnett squares.
Go ahead.
As I said, they're like math Punnett squares.
Punnett squares was developed because of math. It wasn't the other way. I was like, and a Punnett square is actually statistics. It's not this.
It's similar, but not the same.
Yeah, I was like, Punnett squares are a statistics property. Okay, so I have my box, I have it multiplied out. Now I have this equation. Notice the radicals are gone, but this is not solved. So what do we need to do?
Well, we need to isolate X.
Moving to one side, put 0 on.
Remember what, in order to solve a quadratic, you have to get it equal to 0. So it's not our standard linear of, oh, isolate X, because you can't isolate the X. With quadratics, and this is back to what we were doing in chapter 6 and 7. You have to get this equal to 0 in order to be able to solve a quadratic. Minus, what is that for? Once I have it equal to 0, then I should be able to solve this, because what wonderful thing do we get to do now? Diamond. What multiplies to -4 and sums to +3?
4 times 1.
One more time.
Positive 1 times negative. The opposite of what I just said.
Yes.
That's in my head, but I can't get it out of my mouth.
+4 and -1, they multiply to -4, that sums to +3. This happens to be the simplified version of the diamond, because why?
Because X is.
Because the term in front of x squared is 1. So yes, I can go straight to the factors. So once I have my solutions, all right, there is one last step here. We have to check it, and it's because there's extraneous answers. When you square something, all right, you actually add extra answers. You add extra by squared number. Which means that these you need to check every single time. There is no way around this. Unlike the other stuff we've done, so it was a 3 or something, right? 3 is. Unlike the other stuff we've done where I'm like, we did a good job, I tend not to check. These even I check, because one of these, right, is incorrect. I just don't know which one. So let's start with, and usually the negative one actually is the incorrect one. So we'll start with the negative one and we'll see what we end up with. So negative 12, 1 square root, and this is the positive interpretation because it's not resulting in 2 values. So that means that that results in 1 minus 3.
So that one's not.
-2, is that equal to -4?
No.
Nope. Which means that I could do and you could do this quick check in your head, all right? Because let's see, 3 times 1, so that's 16 square root 4, 4 minus 3 is 1, which equals 1. All right, so clearly that's the correct answer. The negative one is usually the incorrect one, but sometimes they're both positive, so you need to check them. All right, so 2x plus 1 to the 1/3 plus 5 equals 0. I want to bring that 5 over because I need to isolate the radical. Also, it's prettier to write it. You can leave it as the exponential power. but it's simpler to understand if you have it written as a radical. So you can make that your first step or simultaneously do that in another step. And mostly we do that because now that I have a cube root, what's the opposite of cube root? Cubing. Negative. Important note. When you put squares and stuff like that in your calculator, make sure you're putting them in parentheses. Right? -5 squared, that's positive 25. If you put it in your calculator as -5 squared, your calculator does order of operations, right? It says exponent, then negative. Okay, so again, just important note with your calculator, but negative cubed, still a negative. Oh, once I have that, this one actually is a pretty simple solve. The trick on this one was just identifying a fractional exponent. Now, even though that's negative, cubes are different. Squares are the ones that end up with extraneous solutions. A cube root is actually better than a square root because it doesn't add extraneous answers, and you can have a negative solution, right? Negative times a negative times a negative does result in negative. All right, one more. So I said the best thing is to isolate the radical. But when you have two radicals, you can only isolate one of them. So typically, it doesn't matter. Pick whichever one is more complicated, which looks like the one on the left. So I want to isolate that one. So the best we can do here is isolate one of the radicals, okay? Because I can't even if I bring this one over, nothing gets better, all right? The best I can do is isolate a single radical, and then I still proceed just like we did before. In order to get rid of a square root, square both sides. So the left side, super easy. Square root of 10 minus x squared is 10 minus x. The right side, this is the beauty. Go ahead.
Okay, well, yeah, that's what I was asking about.
The right side is truly, truly beautiful because what do you think we have to do, Anna?
It would square the 2 and then the radical just goes away, so it'd just be 4 minus 6. Or do you have to do the whole thing? Would it be 2 plus that? Oh, it's the whole damn thing.
It's 2 plus root 4 minus x times 2 plus root 4 minus x, which means when I have a binomial times binomial, what do? Box. Good job. This is where box outshines FOIL all the way because now they're just getting so complex. Doing this with FOIL is where people really start to make mistakes. So this is where the box starts to really shine because so much is going on now. All right, 2 times 2 is 4. 2 times root 4 minus x is 2 root 4 minus x. 2 times root 4 minus x. And at least on the good side, root 4 minus x times root 4 minus x is?
4 minus x.
4 minus x. Now, the nice thing about radicals in the box is that terms actually combine on both diagonals. So this ends up with 4 root 4 minus x, because 2 root 4 minus x plus 2 root 4 minus x. And then I have 4 plus 4, which is 8 minus x. So bringing my 10 minus x down from above, this is what we end up with. Now, does anything jump out? What do we see? What should we do?
We can get rid of the outlier x's.
That is, yeah, let's move the x's over, and while I'm at it, let's move the 8 over. And now what do we see we need to do?
Square it again?
I wanted to finish on a really happy note. We don't have to just square this problem once, but twice, because I have another radical. The only way to get rid of a radical is to do the opposite. Now, be aware, I could divide by 4 first, but actually I want to leave it over there just so you can see this does work. All right, so left side, I square that. That becomes a 4. Now, this actually is 4 squared root 4 minus x squared, right? The 2 goes across each piece when they're being multiplied, not when they're being added. So that becomes 4 equals 16, 4 squared 16. Root 4 minus x squared is just 4 minus x. And then what should we do? Rainbow. And look at that, we're ending the class on basically exactly what we started with. Oh, it's almost like I planned this.
It's almost like you need class.
64. 16 times 4.
4 minus 16.
And then a couple of last little steps.
16 and 16.
Let's see, 38, 15 fourths. And I could verify that, but I do not think we have any extraneous answers, and I could double check that. Negatives are without a doubt the ones I worry about the most, all right? It's always good to check your answers every time. When you end up with more than one answer, that's the time that you want to focus on checking your answers. All right. Oh, what a wonderful problem to end on.
Yeah.
We got the box, diamond, square twice, all kinds of good stuff.
So today are we doing both activity 2 and 3 for chapter 10?
That is correct.